Okay, in this example, what we're going to look at is calculating the momentum change of different objects. In this case, we're going to look at a curling stone and look at how the momentum changes. What that means about impulse, what the net force, average net force acting on the object is, and things like that, based off the lesson we just had. So basically, what we're going to look at here is this 20 kilogram curling stone, which is sliding across the ground at about, or the ice at about 5 meters per second. A little bit of rough ice comes about, and it decelerates at decelerates down to about 4.75 meters per second, and it takes about 0.25 seconds for this to happen. Now remember, change in momentum is very similar, or basically implies that there's an acceleration occurring, and that's why Newton, when he developed his Newton's second law, he really looked at it as sort of a change in momentum, or sort of the momentum impulse theorem. So let's do some basic calculations, just look at what the units look like, look how we can write these momentum changes as an impulse, see how we can figure out the net force and things like that. So first things first, we start out with delta P, so the change in momentum. Well, change in momentum is, in this case, mv2, final momentum, minus the initial momentum. Just like everything else we've ever done, it's final minus initial. Okay? Substituting in our values here, I'm not going to common factor out the m in this case, just so we can look at the units and just get a sense of what's happening. So the final momentum is 20 kilograms times 4.75 meters per second minus 20 times 5 meters per second, which was the initial momentum. So when we work this out, we'll see that we have 95 kilogram meters per second of momentum after it encounters this rough patch of ice, minus 100 kilogram meters per second, which is the initial momentum. So when we look at the final minus the initial, we say, hey, look, it's lost some momentum. Some of that momentum was, went into this rough patch of ice. So the delta P at the end is simply negative 5 kilogram meters per second. That's a change in momentum of this object. Okay. This is very much related to an acceleration of an object, and we'll see what that looks like shortly. But this is how much momentum was changed. State the impulse. Well, the impulse is equal to the change in momentum by definition. So therefore the impulse is negative 5 Newton seconds, like so. Now, why is it 5 Newton seconds? We talked before that the units for impulse are Newton seconds, and the change in momentum is kilogram meters per second. But what I wanted to show you is that since impulse is change in momentum, and the momentum units are, so I'm just going to switch to units now instead of actually writing this out. The units for this are kilograms meters per second, and over here it's newtons seconds. Well, what's a newton? F equals ma says that a newton is a kilogram meter per second, like that. That's what a newton is, 1 newton. So I'm going to rewrite this over here as a kilogram meter per second times seconds. These two must be the same. And in fact, seconds over seconds, and you get kilograms meters per second equals kilograms meters per second. The units work out exactly the same. So what you see is that a Newton second is exactly equal to a kilogram meter per second. So the units are consistent. The units are consistent. So that's really important to understand. Since they're equal to each other, they should be the same. Calculate the average net force acting on the stone during the collision, or during this interaction, right? Because you can kind of think of it as like collision with the rough surface. So the average net force from our previous momentum impulse theorem was that the average net force times the time is equal to the impulse, which is just the change in momentum. Well, what that means is that if we want to find the average net force, we simply take the impulse or the change in momentum, it doesn't matter, divided by time. So either one of these actually works out for us. Now we'll take the first one here, right? Because the units just make it easier to figure out. So we come over here. The average net force acting on this object, the curling stone, is -5 Newton seconds divided by 0.25 seconds. And when we do this, -20 newtons of force. So there's an average net force of 20 newtons backwards on the block, which causes it to actually slow down and decelerate. Okay, well, we can actually calculate this deceleration. It's fairly simple to do. So to calculate this deceleration, we know that the average net force is equal to mass times acceleration. So the acceleration is the average net force divided by the mass, -20 newtons divided by 20 kilograms. Now, thinking about the units again, it's -1 newtons per kilogram, but a newton is -1, so a newton is a kilogram meters per second over kilogram, and we get our answer, as we already knew, that the acceleration would be -1 meters per second. All right. The last part says, what's the sort of the length of through which this patch of like how big of a patch of ice is this? And there's different ways of solving this. In fact, there's quite a few different ways of doing this. We could look at the amount of work that's done on the object. We could look at a kinematics equation. In fact, we'll probably just look at the kinematics equation. It'll be quite a bit easier to do. So one of the kinematics equations we could use is this one here, v2 squared equals v1 squared plus 2a delta d. We could have also used delta d equals v1 delta t plus a delta t squared over 2. That would have also worked. Both are fine because we have lots of information. We have more information than we require to solve this. So v2 was 4.75 squared minus 5 squared all over 2 times -1. And so we get 4.75 squared, subtract 5 squared, divided by, I get about 1.22 meters. So about 1.22 meters is the distance through which the object slows down. So you could have used the time one as well. So if we had done v1, which was 5 times the time, you get 1.22 as well. So whichever equation you use, you get that solution. Okay. So, and we're going to see how this ties into graphing in the next tutorial, how we can actually graph this motion, look at the area. We can look at including some integral calculus in this as well. So I won't go through all of the tennis ball problem. I'll leave this one for you to work out on your own. But let's consider a case where we have two situations, and the ball is thrown against the wall and rebounds. So it comes in at 10, bounces back at 5. And the other one where it goes in at 30 and almost completely elastic and bounces back. So this would be like a kid's ball that you'd start a student just learning how to play tennis. The ball would bounce back at less speed, making it easier to control, and just you can't hit it as hard. And then as you get higher up, you start playing with a real ball, and you see that it comes in at 30, comes back at 28. So we gave it a mass of 0.06 kilograms. In case A, it's less elastic than in case B. The collisions occur for the same length of time, so it's about 0.2 second interaction. And it says make this direction positive just to keep it consistent. Okay, we're going to discover which has the greatest momentum change, the greatest impulse. We know those two are tied together. The biggest acceleration and the largest average net force. Take a minute and think, which one would have the largest change in momentum and which one would have the smallest change in momentum? Think about that. Put it on pause if you need to, and write down or think about which one you think out of this case or this case would have the largest momentum change. Okay, so if you pause that and wrote down A or B, which did you pick? A lot of people pick A because they say, well, it went from 10 to 5. And they seem to say, well, that makes sense. It's the biggest change in momentum. And then other people say, well, it's 30 to 28. That's got a momentum change of 2 or a momentum change of 5? Or am I not thinking about it correctly? Perhaps I didn't take this positive sign into account. So let's take a look. Calculate the momentum change in each case. So case A, right here, change in momentum is mv2 minus mv1. The mass 0.06. v2, the final speed is negative 5 meters per second minus. The other one is 0.06. And v1 is positive 10. So the change in momentum for part case A, I'll put an A here as a subscript. So if we were to do this, negative 0.9 kilogram meters per second. Case B. Okay. Delta PB. Same thing, MV2 minus MV1, 0.06. Now V2 is negative 28. And that's plus 30 because it's moving to the right. So our delta P, the change in momentum, negative 3.48 kilogram meters per second. Part B had a larger change in momentum than part A in case A. And that's because the speed, we had to take into account the directionality. So it's really a velocity, right? And that's hence why we have these velocity vectors written over top of them. So this would be a pretty elastic situation, and this would be less elastic. The more elastic the situation, the larger the change in momentum. All right, well, the impulse for part A is negative 0.9 Newton seconds, and the impulse for part B is negative 3.5 Newton seconds. Calculate the average net force. So as before, the average net force for case A, delta T is the impulse in A. So in this case, the average net force is negative 0.9 Newton seconds divided by 0.2 seconds. 4.5 newtons. Average negative. So there's a negative 4.5 newtons acting on the ball to change its direction and shoot it backwards. For the next one, the average net force delta T equals IB. And this case is negative 3.48 divided by 0.2. We know we're going to get units of newtons. Negative 17.4 newtons. Again, larger force acting on it in order to change its momentum by so much. In order to change the direction and keep it going so fast, has a much larger net force acting on it. Which means that we know the acceleration is going to be larger as well. So in this case, in each case, it's sigma F over the mass. This is our defining equation. So for case A, we know the acceleration is going to be negative 4.5 newtons over 0.06 kilograms, approximately negative 75 meters per second divided by 10 is about 7.5 Gs. Approximately 7.5 Gs. It's a lot. This is quite a large acceleration. Case B, and now you can get a sense of it's going to be quite a bit larger. And this one here, 17.4 divided by 0.06, 290, negative 290, so it accelerated in the negative direction, divided by 10. Remember, it should be divided by 9.8, but it's close enough. It's about 29 Gs, 29 times the acceleration of gravity. That's very large. So to bring this back to the grade 11 course where we talked about collisions and crumple zones, you can see here that if the more elastic the collision, the greater the acceleration, which means that, because you had a larger net force acting on the object in order to change its direction, in order to, get it to hit and bounce back. So in order to have a situation where you want to walk away from a collision, you want the change in momentum to be as small as possible. Okay? So having a small change in momentum is really important, and will definitely affect, in the first case here, the smallest change you could get is that it sticks to the wall. So, it sort of absorb into the wall, in which case you would take your final momentum would be 0, and so you get 0.06 times 10. So you would have got a momentum change of 0.6 kilogram meters per second, which would have been the smallest amount that you could have gotten in that case. Unless you somehow slowed down before you hit it, but we're assuming that interaction, you came to rest about 0.2 seconds. You could go back to the other question and figure out how much compression occurred by using V2 squared equals V1 squared plus 2A delta D, and you could figure out how much of the compression occurred in that 0.2 seconds of the ball in each case. You'd find that the second one probably compressed a lot more, and in case B it probably a little bit less. Okay, so that's the basics of momentum and impulse before we get into looking at force time graphs and how they relate to this as well.